at another. Same question. And we have, let's say, 4. Oh, this is not a good color. We have negative 4 x to the third plus 5x squared plus 8. And we are interested in whether x plus 3 is a factor or is not a factor, on page 4, of this polynomial. What do I have to do? We're not asked to find the quotient. We're only asked to find quickly whether x plus 3 is a factor of this or not. What do we need to do?
Wait, so would you want us to do this without long division?
Yes. Yes. Using the factor theorem and the remainder theorem. Yes. So let's go back. Look at what we did before and let me know. What should we do? To check whether it's a factor or not. Anyone, please?
Would you plug 3?
So when we had x minus 2, we plugged in 2. This time, in this polynomial, p of x, what are we going to plug in?
-3?
Yes, indeed, -3. Indeed. -3. So we have -4, -3 to the third, plus 5 times -3 squared, which I already know it's 9, and plus 8. So this is -27, 45 plus 8, and this is positive what? I think 108, correct me if I'm wrong, and plus 45 plus 8, I don't care, it's not 0. What do we conclude? Is x plus 3 a factor of p of x or not?
It is not a factor.
Not a factor. Not a factor. Do you feel better about the remainder theorem and the factor theorem? So the remainder is definitely this number, this sum. So let me finish it up then. So 116 plus 45, we get 161. This is indeed the remainder. There is no discussion. We found the remainder. We don't have the quotient. In order to find the quotient, we have to use synthetic division or we have to use long division. But this is for sure the remainder of the division. There is no discussion there. Because it's not 0, the factor theorem tells us that this is not a factor. The remainder theorem says that it's not a factor. Any questions? Are we okay with the factor theorem and the remainder theorem, or do we need another example? Is everyone okay with this?
Yes.
Okay. So, final thing before we look at rational functions, which is a major topic. Last thing is something called rational zeros of polynomials. You can say we have that in the graphing calculator, that app, and why are you teaching us this? I have the app, I'll go to the polynomial number 9, I'll put in the polynomial that I need, whatever degree, I punch it in, and it's done. Why are you teaching us rational zeros of polynomials? Who cares? Well, if you ask me that question, I have to answer. And my answer is, no, it's not going to be a silly answer like, what if you forgot your calculator? No. It's like transformations and like symmetry. These are properties of polynomials. So finding rational zeros when we need them, it's an important method, I would say. Is it super important? Maybe not. Is it super useful? I would say you can check with a graphing calculator, but I think it's an important topic to know. As I said, not top of the line important, but an important, like as I said, symmetry and transformations. So here's what it is. I think you're going to like it. It's an interesting puzzle, more or less. I'm going to choose a problem. It doesn't matter. And then you choose the next one. So let's say I'm going to look at 46. So we have a polynomial or a function, doesn't matter, same thing, 8x squared plus 11x minus 20. And what does it mean by rational zeros? So remember when we had a quadratic function, we are able to find solutions right away. Yes, with the app and the calculator, but we have other options. We have factoring, we have a quadratic formula, we have other possibilities depending on the polynomial, on the quadratic. But now, when we move on to higher degree, we're kind of stuck. I don't know how to factor this. I don't know what to do with this, right? But I can still find something called rational zeros. By rational, I mean 1/2, negative 3/4. This is our rational zeros, right? Which I may not be able to factor anyway. And I don't even know how and where to start here, right? But we say the following. If this polynomial has rational zeros, they must be on the following list. Negative 20 divided by 1. Factors of this. Positive, negative is really not important. What are the factors of 20? Okay, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. A lot. What are the divisors of 1? Okay, plus or minus 1. So because it's 1 in the denominator, I'm going to disregard it. It doesn't make any difference. So these are the possibilities. 20 over 1. And all possible factors of 20 in this case. If this were 3, then I would have had plus or minus 1 over plus or minus 3, plus or minus 2 over plus or minus 3, plus or minus 4, and so on and so forth. How do I do this? Using the remainder theorem. Plug in the function, this number, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5. And if I ever get 0, I'll say, oh, I found a solution. Now, how many solutions can it have? At most, how many? Max.
3?
Exactly. Maximum 3. Thank you. So, I will punch in the graphing calculator. Here is my y equals. In y equals, I clear everything, and I put in this function, x to the third. If I don't find any zeros, then it doesn't have any rational zeros. was plus. So x squared plus 8x squared, x cubed plus 8x squared, sorry, plus 11x, and minus 20. And then I go with second and table. Make sure that you go first with second and table set, and make sure that your independent variable is in the ask mode, not the dependent though. Only the independent in the ask mode. So you can punch in the numbers you want. And what numbers do I want? Oh, of course, negative 1, 1. Ah, I found 1. When I plugged in 1, so x equals 1 is the first solution. Good. I'm plugging in positive 2, negative 2, positive 4, negative 4. Ah, excellent. I got another one. X equals negative 4. Okay, moving on. Positive 5, negative 5. I only look for one more. That's it. I'm done. I don't care for the rest. No matter what I do, you cannot have more than 3 solutions or 3 zeros. X equals 1, x equals negative 4, and x equals negative 5. Yes, you can always, just in case, just to double check, if you want, you go to the poly, you go to degree 3. Careful how you enter the coefficients. The first one is 1. The next one is 8. The next one is 11. And the next one is negative 20. When I hit enter, I have to get negative 5, negative 4, and positive 1. Mandatory. Okay? So we obtain them in a different way. How? Using the rational zeros theorem. How? We made a list of all divisors of this over all divisors of this. The divisors of this are plus or minus 1, ta 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 ta. The divisors of this are plus or minus 1. I disregarded them because they will not make any difference. So I checked plus 1, negative 1, plus 2, negative 2, plus 3, plus 4, negative 4, blah, da, da, da. I didn't even get the chance to do more because I already found 3 solutions as expected. And it's done. I think we should look at one more example, but let's see if you have any questions first. Any questions about this method of finding rational zeros?
Wait, can you show like how you plug them into the table? On
Yes, 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 of course. Okay. So first I enter the function. The function has to be correctly entered, right? X cubed plus 4, 8x squared plus 11x minus 20. Then make sure that you go to second and table set. And make sure the start, the increment, these mean nothing. But the independent variable has to be in the ask mode. If it isn't, just scroll down, go to the right, and press enter. Because if it's not in the ask mode, the calculator will not allow you to enter the numbers you want to enter. And after you do that, then you go to second and table, and you just plug them in one by one. Positive 1, negative 1, positive 2, negative 2, positive 4, negative 4, and so on and so forth. I did not have to continue. There are no more solutions. It's not possible because I found 3, and the degree is 3. Is this better?
Yeah, that clears it up. Thank you.
Perfect, perfect. Other questions for me? Okay, let's work on one more just to make sure that this is super clear. Okay, let's say 48. And then we can move on to rational functions. So we have f of x equals 2x cubed plus x squared plus 2x plus 1. If this polynomial has rational zeros, they will be among the list of 1 over 2. Factors of 1, oh, just this. Factors of 2, plus or minus 1, plus or minus 2. So what is the complete list of what I'm going to try? this over this, which is still plus or minus 1, this over this, which is plus or minus 1/2. This is it. So factors of 1, plus or minus 1. Factors of 2, plus or minus 1, plus or minus 2. In general, I mean, in summary, I should say, this over this is this over this is this. So I punch in the new polynomial in y equals, I clear, now I have 2x cubed, and then plus x squared plus 2x, and then plus 1, and I go to second table. I can only check -1, it's already there. Then I'm checking 1, it's already there. I'm checking -0.5 or just 1/2, whatever you want to write with, it's the same. Ah, awesome. X equals -1/2 is one rational 0. And now I'm checking +2. No. Oh, I'm sorry. I have to check 0.5, sorry. No. So +1, -1, no. -1/2, yes. 1/2, no. So this is the only rational 0. What does it mean? That the other two are, they may exist or may not. We'll see in a moment, we can check. But they are not rational. This is rational, but x sub 2 and x sub 3 are not rational. They may be imaginary or they may just be irrational numbers. 1.2, 3, 5, 9, and so on and so forth. And we can check. We go to apps again. And I didn't mean that. I meant to go to apps. And then 9. And it's a polynomial degree 3 as well. Coefficients, the first one is 2. The leading coefficient is 2. The next one is 1. The next one is 2. And the last one is 1. When I hit enter, I have to get -0.5. And 2 others, I don't know what they are. Aha! Imaginary. So we did get a real solution, -1/2. And we didn't know what x sub 2 or x sub 3 were, but definitely not rational. And it turns out that they are imaginary. So this is like an interesting puzzle, basically. Just look at it as a puzzle. The divisors of 1, plus or minus 1, over the divisors of 2, plus or minus 1, plus or minus 2. And these are the only options. 4 options, plus or minus 1, this division, and this division, plus or minus 1/2. Nothing worked except -1/2, and the other 2 were not in this category. And it turns out that they were imaginary. And this theorem is only for rational zeros. A rational number can be 2 or 5, right, as we had before. This is a rational number. It's 1 over 1. This is a rational number, -4 over 1. Rational number, -5 over 1. Okay, finally, before we look at word problems,